this video is about the Chatelier's principle. Bear with me for the pronunciation. Okay, so for the Chatelier's principle, the idea is, right, so you will have a stress to the equation at equilibrium. Okay, so that means the equation already reaches equilibrium. Okay, and then now you're adding some stress. The stress could include, right, the change of concentration of the reactants or the products, or you're changing the pressure. And then again, if you're dealing with gas, right, so when you change the pressure, the volume as a result will also change. Okay, and then the third type of stress could be changing the temperature. Okay, and then the last stress will be adding inert gas, right, or a noble gas, right? Okay, so and then how they are gonna affect the equilibrium, the equilibrium for this reaction. Okay, so therefore now let's look into it. Okay, so for this question, of course, during the quiz, I'm not asking you for all of this. Okay, so I'll pick out some of this and then you're gonna answer. Okay, so that's for that. Okay, so now let's start looking into this. Okay, so for this particular equation given from this question, right, so you have this reaction equation and then it's telling you delta H not equals to positive 92.4 kilojoule. Okay, so remember, we learned this before, right? So we know that tells us delta H now equals to Q at our constant pressure, right? So that means the Q is positive. Okay, so not degrees Celsius. Q is positive, which means what? It's gonna absorb heat, right? So this reaction is an endothermic reaction. Okay, so it's an endothermic reaction. Okay, so that's something to keep in mind. Okay, and then also, of course, during a quiz or the exam, I could give you, actually just tell you, without giving you the actual number or the sign, just tell you this reaction is endothermic. Then you know if it's an endothermic reaction, the heat is as what? As, let's actually use right? So it's heat, right? So heat will be part of the reactant, right? Because it's endothermic. You need, right? You need the heat in order for the reaction to happen. Okay, so that's something, again, automatically when you see endothermic, you know heat will be part of the reactants. Okay, and then if you have exothermic, the heat will be part of the products. Okay, so that's something, again, keep in mind. Okay, so now let's look at under all these conditions, the equilibrium will shift to which direction. Okay, so for the first one, okay, so you're gonna remove N2. Okay, so that means N2, let's actually use the same color. Okay, so you're gonna remove N2. Okay, so you're gonna reduce some of N2. Again, the system, the reaction equation is trying to counteract this stress. Okay, so if you remove some, the reaction wants to make a little bit more to make up whatever is lost, right? So if we want remove some, so that means you're gonna make more, so the equilibrium will shift to the right. Okay, so shift to the right. Okay, so that'll be the first one, right? So basically removing N2 is removing the products, the equilibrium will shift to the right. Okay, so now let's look at the second one. The second one is adding H2. Okay, so you're adding more of H2. So now the stress, you added more of the H2. So originally, right, it's already at equilibrium, you added more of the product. So now the system tried to counteract that. So what do we need to do? We need to use some of that, right? So in order to use the product direction will be shift to the left, right? Okay, shift to the left to use some of the H2, right? Okay, so that's the logic. Okay, so that's the second one. Okay, and then let's keep on going. Okay, so for adding NH3, okay, NH3 is what is the reactant. Okay, so you added more of the reactants. As we said, that's the stress to this equilibrium, right? So in order to counteract, we're going to use some of NH3, so the reaction will shift to the right. Okay, so in order to use some of the the reactants. Okay, and then the next one will be removing NH3. Okay, so now you remove some of the reactants. Okay, so you're gonna remove some of the reactants, so that means you have less. Okay, so in order to counteract, you're gonna make a little bit more. So in order to make more of the NH3, the equilibrium is gonna shift, yes, to the left, right, to make more. Okay, so that's this one. Okay, and now let's keep on going. Okay, so before we keep on going, if you look at these 4 conditions we just mentioned, so what are they? They're changing of the concentrations, right? Changing, either getting more of the reactants or remove, or adding more of the products or remove some of the products. Okay, so you just need to know, again, the logic behind it, right? So once you have the stress, you're gonna counteract. Okay, so just say one more time, like the first one. If you're removing, you take some out, right? You remove, take this out, so that means you have less. In order to counteract that, you're gonna make a little bit more. Okay, so in order to get more of a N2, what do we need to do to have the reaction shift to the right to make more? Okay, so that will be the first category actually. Okay, so that will be the concentrations of our reactants and products. Okay, so that's for the first category. Okay, so before we move on, actually, okay, so I know this is a guess, but what if, just say I have as solid, just say, and then what about that? Okay, what if I say I'm gonna remove some NH3, but it has the status or the states as solid? Then you go, well, I remember solid and liquid, yes, they are not affecting the equilibrium constant, right? So you don't worry about that if it's solid. Okay, so that's for that. Okay, so now let's keep on moving. Okay, then we're gonna have about pressure. Okay, so remember, for pressure and volume, right? So they're related. Again, for gas, right? For gas, what do we have? We have PV equals to nRT, right? Okay, so that's ideal gas law for gas. Okay, so again, for gas as a particular or as a special characteristic properties. So what is it? Is the gas molecules moves really fast, right? So they will have these collisions with each other and with the surface of the container. So they're exerting a pressure, right? A force. That force we divided by the area that's giving us pressure, right? Okay, so the pressure is related to volume, right? So the relationship between the pressure and volume is what? Is inversely proportional. Okay, so that means when increase, the other one will decrease. So which means if you increase the pressure, the volume will be decreased. Okay, so think about it, right? When you have a party, right, you have helium, okay, and then helium in the tank, right? So basically we are reduce the volume and then the pressure is increased, right? So when you increase the pressure, volume is decreased. The other way around, when you decrease the pressure, the volume is increased. Okay, so they're inversely proportional. Okay, so therefore, then you go, oh, now I see if that's the point. Does that mean if we have increased pressure, then you should have the same conclusion as decreased volume? That's correct, because when it's true, when you increase the pressure, that equals to you decreasing the pressure. When you increase the pressure, that equals to decreasing the volume. Okay, so those two actually should have the same conclusion. Okay, so now let's see, when you increase the pressure, or which also means decrease the volume, what's gonna happen? Okay, so as we mentioned during the lecture, when you decrease the volume, that means just say we are assigned with an even smaller room. So what's gonna happen? People is gonna be more packed, right? You're gonna be right next to each other, right? So you have a smaller room. Okay, so one way could counteract that is that we're gonna have less. If we have less people, that could be one of the solutions, right? So in terms of this reaction, if you have the reaction, if you will have smaller room, if you increase the pressure, which means you have less volume or decreased volume. Okay, and then what's going to happen? The reaction is going to shift to the direction with less moles of the gas. Okay, so I say one more time. Okay, so those two. Okay, so those two, I'll put it as a conclusion. Okay, so as a conclusion. Okay, so it's gonna move, the equilibrium is gonna move to less moles. Okay, so it will be the same conclusion for this, right? Because when you have decreased the volume. Okay, so now let's look at our reaction equation. Okay, so on the left side you have 2 moles, on the right side you have 1 plus 3. Let's give us 4 moles of the gas. Okay, so 2 compared to 4, right? On the left side that will be less moles. Okay, so when you have increased the pressure, and it's gonna move, the equilibrium is gonna shift to the left, to the less moles of the the side, right? Okay, so that's the left. Okay, as we said, when you decrease the volume, you're gonna have the same conclusion. Okay, so that's for the first two. Okay, and then accordingly, I believe you already know what the answer should be for the other two. Okay, but let's actually take a look again for the other two. So decreasing pressure will actually is the same as what increase the volume. So again, they come along with each other. When you decrease the pressure, okay, so that means you can have more room, and then when you have more room, you can fit more people, right? So therefore, you can fit more of the reactants or products, wherever the site has more. Okay, so therefore, okay, so over here it's gonna move to more moles. Okay, it could be, again, like I said, either way. Okay, whichever side has more of the moles. Okay, and we already calculated that on the left we have 2 moles, on the right side we have 4 moles. Okay, so therefore we have more room, which will be the increase of volume, so it's gonna move to the right side. Again, having more room, that's also is result in with the decreasing of the pressure. Okay, so you probably see, okay, yeah, this for their set, right? So they're talking about pressure and volume, how they're affecting the equilibrium. Okay, so when you have the stress, how the system is gonna counteract. Okay, and then if you again recall what happened during the lecture, right? So we say the first two situations, right? The K equilibrium constant doesn't change, right? It doesn't change. Okay, so the system will counteract and will re-establish the equilibrium. Okay, and the same one, the K doesn't change when you change the pressure or volume. Okay, and then when the equilibrium constant change, yeah, you probably it's coming up. Yes, it's over here. Okay, what color would be? This one. Okay, so this too, the temperature, K will change. Okay, K will change. K changes. Okay, when you change the temperature, as I keep on saying, right? Temperature is a troublemaker. When you change it, a lot of complicated things happen. Okay, and then equilibrium constant also change. Okay, so let's see how we're gonna talk about this. Okay, so now let's see for this particular equation. We already figured out there's a endothermic reaction because delta H is a positive value, right? So the heat will be part of the reactants. Okay, so now if you increase the temperature, that means you're going to increase the heat, right? Increase heat. Heat is what? Part of the reactants when you have it as endothermic, right? Okay, so that means when you increase heat, the stress added to what? The left side of the reaction. Okay, so as part of the reactants, so in order to consume that heat, what's going to happen? The equilibrium constant is going to shift it to the right side. Okay, so it's going to shift to the right. Okay, to consume that heat. Okay, so I move it to the right. What's going to happen? That means the reaction lays far towards the product side. Okay, so that means K will what? Increases. Okay, and then you will have the other way. Okay, so if you had decreased the temperature, so what's going to happen when you decrease temperature? Then it's also you can think it as taking some of the reactants out. Okay, so then again, the stress is you have less of the reactants. So what's going to happen? The equilibrium is going to shift to the left, okay, to make more, right? Okay, to make more of the reactants. Okay, and then therefore now you realize the equilibrium is shift to the to far towards the left side, towards the reactant side, and that means K is decreases or decreasing. Equilibrium constant decreases. Okay, so that's what we have for changing the temperature. Okay, so what's gonna happen? Okay, and now the last one is easy, right? So the last one is when you add argon. When you add argon to the system, what's gonna happen? Okay, so argon is an inert gas. Okay, so in this case, it's not gonna affect, right? It's not gonna affect, no effect to our equilibrium. Okay, so it's not gonna shift. Actually, let's just do one more condition, right? So one more situation could be, what if we're adding a catalyst to the system? Okay, so remember, catalyst, we have both, right? The positive catalyst, which is making the reaction goes faster, okay, and then you also have the negative catalyst, which is making the reaction go slower. But again, that's not the point for this question actually, but you have to understand by adding the catalyst, you will affect both the forward and reverse reaction rate at the same speed. So basically, you will have to say you're making the reaction goes faster, and then the forward reaction go faster, and then at the same rate, the reverse reaction will go faster as well. So as a total effect, right, there will be actually no effect on this equilibrium. Okay, so actually there's no effect. Okay, and then just readdress on catalyst. Okay, so catalyst actually changing the mechanism of the reaction. So the reaction is going to happen in a different route. Okay, so before, just say you have large activation energy. Again, we're talking about the positive catalyst. You're making the reaction goes faster. Okay, and then right, so when you're making the reaction goes faster, which means you lower the activation energy. Okay, so therefore the reaction can go faster. Again, that faster works both directions, so that's why, again, adding a catalyst excuse me, there will be no effect on the equilibrium. Okay, so that's all for this video, and hopefully this is helpful, and thank you for your time, and thank you for watching.